All right, welcome back to Chem with Com. This is our last video for stoichiometry. Again, it's really focusing on the mole ratio. Um, and this is our last video called Quantitative Chemical Analysis. This is a four-part series. Do not start here. Go back to stoichiometry basics to get you prepped for this kind of harder stuff. Right? This is a direct continuation after limiting reactants. So yeah, let's get on it. All right, let me just clean up my screen a little bit. All right, let's go for it. So we're now going to expand on our conversion table. What's new is this stuff up here. We're going to now incorporate the molarity equation. And this is the same thing down here, right? Just for, remember, it's one thing, atom or molecule, and the second atom or molecule. They're going to be on opposite sides of that dashed line. We're going to use a molarity equation to convert volume and molarity to moles, change out moles, and go to the other volume or molarity. So yeah, let's just get started. Again, if you've never seen a version of this conversion table before, go back a few lectures and you'll see it, and that'll give you the information to continue using this. All right. So let's do this. I have a little diagram here. So we did this before, but we're going to do this specifically for this diagram here, for this conversion diagram. So the question is, what volume of 0.0105 molar HBr solution to titrate 125 milliliters of a 0.0100 molar calcium hydroxide solution? All right, conceptually, what's happening is we're using this base, right? The base is the calcium, and remember, hydroxide is the base part. And what we're doing is we're neutralizing that with an acid. This is our acid here. And the H part is the acid, right? So we're neutralizing an acid and base. They're telling us we have this many milliliters of calcium hydroxide at this concentration. Here they're telling us we have this concentration of acid, but we are supposed to find the volume. Oops, I can't spell volume. We are trying to find the volume. Okay, so we're going to, step one, write one reactant or product on one side of the dotted line. Well, we marked it, we put it here on this side of the dotted line. Write the other reactant or product on the other side of the dotted line, so HBr. We always want to start with the reactant or product with the most information. This had more information, so that's what we're starting with. So I'm going to put here our start, and then we're going to end because we're looking for the volume of HBr. All right, so we're going to use our volume, which is the first thing, and our molarity to calculate moles, right? Sorry, we labeled our start endpoints, and then we're going to move through the boxes. That's what we're doing now. So once we're at moles of calcium hydroxide, we're to convert to moles of hydrogen bromide or hydrobromic acid, right? Because it's aqueous. Once we're there, we can now go to volume because that's what we ultimately want. That's our end goal. So we're going to go right there to volume. All right, let's try it. So here we're starting off with 125 mils. We need to convert to liters because molarity is always in liters, liters, liters. This is liters. So we need to convert the 125 to liters. All right, so we converted that to liters by multiplying by 1 liter over 1,000 mils. The mils cancel out, so we're left with 0.125 liters of calcium hydroxide. We're going to go down this first arrow and convert to moles. And if we look, if we're trying to convert to moles, we need to do the molarity times liters. That's what we did. This is liters, molarity. So this is now moles, right? Once we're at moles of calcium hydroxide, we need to do the mole ratio of HBr, which is 2. Sorry, it's a little messy up there. Let me clean that up a bit. Let me just erase some of this so we can show you the mole ratio, right? This is 2 hydrobromic acid to 1, since there's no coefficient, it's 1 calcium hydroxide. All right, so that's the mole ratio, and we're continuing over here. We got 0.00250 moles of hydrobromic acid. That's how many moles it took to neutralize 0.00125 moles of calcium hydroxide. And it's true because it's a 1-to-2 ratio, so that works for us. All right, now we're just going to carry this over because now we need to figure out volume, right? We need to find volume, which is liters, and it's moles divided by molarity. But where do we get that molarity from? Well, it was given to us at the beginning of the problem. We just didn't use it till way, way later, right? So it's going to be right here. So we do 0.00250 moles HBr divided by 0.0105 molar HBr. And that is now our answer is 0.238 liters, or if they want it in milliliters, you can convert to milliliters. All right, complicated stuff, right? But we're going to use this table to simplify our lives, right? So let's try one right now. The end point in a titration of a 50 milliliter sample of aqueous HCl was reached by addition of 35.25 milliliters of 0.250 molar sodium hydroxide titrant. That's a very, very complex question and statement, right? Or that's just a statement. The question is, what is the molarity of the HCl? Well, let's break this down. We're using HCl and we're looking and sodium hydroxide. Let's write that down here. I'm just going to move this down a bit so we can start working with these numbers here. HCl aqueous plus NaOH aqueous. How did I know to use those? I looked in the equation and I said, hey, they're using HCl and sodium hydroxide. So that's why I know those are what we're going to be using. All right. So I'm going to basically what they're looking for, I'm going to set this over here as, let's write down all the information we have of this, right? This is 50.00 milliliters. Here we have 35.23 milliliters, 35.23 milliliters of 0.250 molar sodium hydroxide. And we don't know what is the molarity. So now this is our ask. They're looking for the molarity of the hydrochloric acid. All right, let's set this up. We want our starting point to be whatever has more information. That has more information here. So HCl is going to go on the bottom. We're starting off with volume and molarity. So this is our start. We're going to go to moles of, draw 2 arrows, moles of sodium hydroxide. Then we're going to cross arrow 4. We need the mole ratio because then we're going to have the moles of hydrochloric acid. And then the end game is molarity of hydrochloric acid. So let's just start. Let's not even mess around here. All right, so let's do this. So in order to start, we're going to use molarity times liters, but we need liters, so we have to do 35.23 mils of sodium hydroxide. We need to change that to liters, right? Mils cancel out, and we have now liters of sodium hydroxide. All right. So now we're still here. We just converted to liters, but now we have to go to moles. So this is going to be now, um, that's going to be liters. Now we have to multiply by the molarity, 250 molarity sodium hydroxide. All right. So now we are actually, you know what? Let me do this in pieces and then I'll come back and I'll do it in one swoop on the next one, just so you can see an example of it doing it piece by piece. All right. So this is now 0.035, 23 liters NaOH. So now we have liters. We have to multiply that by molarity of sodium hydroxide. Let's see what we get. So, and another thing here, right? Molarity, I'll put a little arrow here. I'll show you where the units cancel out. Molarity equals moles per liter. So this M is actually can be replaced with moles per liter. So if you look, the liters cancel out and we're at moles now. Moles, NaOH. All right, so let's do that math. Let's change. So 0.03523, 0.03523, I believe. 0.0353, yep, times 0.250, 0.0088075, 0.0088. We probably didn't need that many numbers, but just to be safe, actually, no, I think we needed them all. I'm just going to rewrite this so it's kind of all in the right order. Moles of NaOH. All right. So now we're at 0.0088075 moles of NaOH. We're here. We need to move to now moles of HCl, so we do the mole ratio. But if you look, it's a 1-to-1 because they don't have numbers. There's no coefficients. So this is going to be 1 mole HCl. This is 1 mole NaOH, sodium hydroxide. These cancel out. And we're left with 0.0088075 moles of HCl. So now we're here. Now we have to go to molarity. We're trying to find molarity. It's now moles divided by liters. Now let's convert this. We're going to go from 50.00 mils times, and this is 1,000 on the bottom, 1 liter on top. That's going to be now 0.050 liters. So that here, 0.050 liters of HCl. So it's 0.0088075 divided by 0.05. And we got, oops, I messed up. 0.0088075. Messed up again. 88075 divided by 0.05. And we got 0.176. We need 3 significant figures because this is 3. 0.176 molarity of HCl, sorry, HCl. All right, let's take a look, make sure we did that correctly. All right, looks good. All right, let's do this again. And I'm gonna, instead of stopping in places and putting the equal sign, I'm gonna do one long equation to show you how kind of you can go through this, right? All right. And it looks harder too, which is good because it's gonna give you some tools. All right. So 20 mil sample of aqueous oxalic acid was titrated with a 0.09113 molar solution of potassium permanganate, KMnO4. This is the net ionic equation they came up with. And they tell you a volume of 23.24 was required to reach the endpoint. What is the oxalic acid molarity? Let's just rewrite this. Again, and we're only going to use the stuff we're going to use. So this is KMnO4. This had a K in front of it, but because it was a spectator ion, we leave that out. If you need help with spectator ions and net ionic equations, see, I believe it was topic, I want to say 9. I think it was called chemical equations and chemical reactions, but let's write this out. 2 MnO4, 1 minus, right? Plus, and they're looking for the oxalic acid. 5 H2C2O4. All right, so here we have our mole ratios. Let's write down the information they give us. They say it's a 20.00 milliliter sample of oxalic acid, and it was titrated with 0.09113 molar solution of potassium permanganate. What, and it says a volume of 23.24 mils was required to reach the endpoint. What is the oxalic acid molarity? That in itself was hard. Taking these words, making them into some sort of number format so we can use those in our flowchart. Let's figure this out. Since this has more information, this is what we're going to start with. MnO4 1 minus, and this is oxalic acid, H2C2O4. We have a volume and molarity. We're going to convert that to moles of manganate or permanganate. Then we're going to go to moles of oxalic acid, and then they want the molarity. So we're going to go to the right again. And we're going to use this equation here, right? But you can, again, this is a very mobile table, conversion table. You can go anywhere you want as long as you have the right conversion stuff. All right, let's now do this in one giant operation. All right, so we're going to convert this into liters because we need liters to use the initial equation of finding moles. So 23.24 mils of permanganate, or MnO4 1 minus. We have 1,000 mils to 1 liter. That gives us liters of permanganate. We're going to multiply by 0.09113. Again, this is molar, so we can call that moles per liter. And let's give this MnO4 1 minus. I'm going to write this as a big, long fraction. Liters of MnO4 1 minus. All right, let's just pause, cancel stuff so we don't get confused of what's there, right? Milliliters and milliliters, right? Liters, liters. permanganate, permanganate. And we're left with moles of permanganate. All right, let's just now continue. We're not going to stop the equation. I'm just stopping to verbalize what we're doing. All right. So now we're at moles of permanganate. We need to go to moles of oxalic acid. So we find the mole ratio. We know there are 2 moles of MnO4 minus. That's 2 here. And we have 5 moles H2C2O4, which is oxalic acid. Again, I'll pause to cancel some stuff out. This cancels out with this, moles of permanganate. All right, now let's look where we're at. Now we're here. We need to go to molarity. For that, we need to figure out the liters because we need to do moles divided by those liters. Right? So it's going to be 1 over, let's bring this down here. Trying not to get in the way of stuff. 20.00 mils, right? Times, let me make this more clear. Let me just put an equal sign there. Let's finish this up. 23.24. Go back to this one, clear this. 23.24 times 1 over 1,000. So parentheses, 1 divided by 1,000. Close parentheses, multiply. 0.09113. 0.09113. And then times, open parentheses, 5 divided by 2, close parentheses, enter. 0.005295. We'll say moles of oxalic acid. 0.005295. Perfect. Okay. All right, let's finish this up now. The bottom part, we're going to convert this into liters because we need things in liters because our equation is in liters, right? Molarity equation uses liters. So mils cancel out, and now we're at 0.020 liters. That's now going to be here, 0.020 liters of, this is specifically oxalic acid. So we're going to do 0.005295 divided by 0.02. And I got 0.26475, 0.26475, and we'll say molarity of, it's a little cramped here, but we need, let's see, 4 significant figures, 4 and 4. 4, right? So we need 4, so it becomes 0. We'll say 4 sig figs. 0.2648 molarity of H2C2O4, which is oxalic acid. All right, that was a doozer. Look how far we've come through the semester, right? This is a crazy looking conversion table. Now we know how to use it. Let's just check the answer real quick. Make sure I'm not doing anything wrong. 2648. Perfect. All right. Looking good. Well, that ends our video here. If you need anything, let me know. But yeah, that wraps up stoichiometry. We have 2 more topics left, gases and acids and bases, and I will catch you later. Thank you very much.